All right, let's begin again here. So you might be thinking with this chi-square test, how much do you have to know for the final exam, or how much do you have to be able to do? You should be able to understand it well to do all of it. However, on a test question, I try to figure out ways to help you save some time. If we were doing a full type of problem like this, perhaps with the expected table, maybe I'd give you 3 out of 4 numbers or 5 out of 6 numbers in the expected table, and you have to calculate one of them. That's not given to you. Maybe I'd give you in the formula for the chi-square statistic, maybe I'd give you, 3 or 5 or whatever of those fractions, and you'd have to calculate one of them to show me you know how to calculate it. Maybe I'd then give you the value of chi-square, and then you just have to know how to use the table based on the appropriate degrees of freedom. So I would try to do things to help save time, because otherwise it can just take up too much time. Okay? So you should understand everything well enough that you can do any of these calculations, but I would do things to help you save time on the final exam. All right, let's go back on to chapter 10 in regression again. I know I did the quick review of regression before the quiz very quickly. So let's go slower. Again, let's look at the regression model. There we go. It is important to have in your mind what's going on here. Okay? Even though you look at this kind of thing and you feel like your eyes are glazing over, you feel like falling asleep, strive to understand what's going on here. It is an important aspect of really being able to use the ideas in chapter 10 in significant ways. Focus on the equation. Here's the way I think of it. It's not actually exactly described in the way that the book is describing it here. You've got population data, not sample data, in your imagination. Okay? Imagine the population data is out there, a bunch of individuals, maybe millions of individuals from the population. They have X and Y values. For each individual, you've got one point, one data point, an X coordinate and a Y coordinate. You're assuming that there are two numbers, beta 0 and beta 1, such that if you, for any given population data value, if you know the X value, you can predict the mean of all the Y values by plugging that X value into this expression right here in place of the Xi. Think of Xi as a particular X value that you're thinking about plugging in. Take beta 0 plus beta 1 times Xi. And that will give you the mean of all the Y's. In fact, they emphasize that here. That expression right there is the mean of all the Y's for that given value of X. You're assuming it's a linear relationship. But that formula gives you the exact mean of all the Y's for a given value of X. You imagine stacked. A stacked scatter plot, really. A bunch of points above a bunch of individual values of X. For any individual value of X, you have a bunch of Y coordinates. You're assuming this equation gives you the mean of the Y's for any given X. It's an assumption you make. Is it true? Probably not. In fact, it's almost a guarantee that it's not true. Exactly. With modeling, you just hope it's good enough. Okay, you hope it's reasonable. It would be very, very unlikely that for every X, the mean of the Y's can be evaluated by some equation like that. But there is still some beta 0 and beta 1. There are population intercept and slope that you could theoretically calculate from the population data if you had it. Whether it would give you the mean of the Y's is the other issue. That's less sure. But you assume it's true. This thing right here, that Greek letter, that's called epsilon. That's the so-called randomness term. It's really a random variable. For any given X, you can determine the y of one data point as a sum of two terms, take the mean of the y's, and add a randomness term. Now, you don't know what that y value is going to be. And in fact, as a random variable, it's really just modeling the randomness in the y values. If you apply this for many different epsilons, many different, if you did simulation, okay, if you used equals rand or something on the spreadsheet to do simulation, to simulate many different values of epsilon, that would model how the y values in the population are distributed, which really means y, at least in terms of how I think about it, is also a random variable. This is a random variable, and this is really a random variable. The book is not treating the y there like a random variable, it's treating it like a second coordinate of the data value. But really it's better to think of it as a random variable, it's got a distribution. Anyway, the epsilons as a random variable are normal. The epsilons are independent of each other, they're unrelated for each time that you use the equation, essentially. It's unrelated to what happened before. They're normally distributed with a mean of 0 and a standard deviation of sigma. Each epsilon I is normal with a mean of 0 and a standard deviation of sigma. What's sigma? We don't know. It's just some positive number. We'd like to estimate it. That's the regression standard error. We're assuming it's the same sigma no matter what x is. For all these stacks in the scatter plot for different values of x, stacks of points, we're assuming the variability in the y values is approximately the same by assuming these normal distributions all have the same standard deviation. And that's where this picture comes in that I showed you before the quiz. Having the right way of thinking about this is important. For any given x, we're looking at 3 specific x values here. You've got to think about this picture in kind of a 3D way with perspective, and I didn't do a great job of that. For each of these given x values, pretend this is 10, 20, and 30 or something. Hours of training time. You've got a bunch of different people from the population who can do a bunch of different entries per hour. There would be a bunch of points with the same x coordinates, but a bunch of different y coordinates. These normal curves would be then modeling the variation in those y values. And because they're normal curves and they have a peak, most of the y values are going to tend to be near the mean in each case. But there will be some more outliers that are 2 or 3 standard deviations away. In each case, for each of these values of x, you assume the standard deviation is measured by this distance is the same. That's an assumption you make in the model. In real life, it doesn't fit it exactly, but you hope it's good enough. Though you should look at graphs to assess whether it really is good enough or not. Once again, the regression standard error, this thing, approximates the standard deviation in those normal curves. S is square root of 1 over n minus 2 times this summation. These are the squares of the residuals. This summation is SSE, sum of the squares of the errors. Errors, again, being synonymous with residual. That's SSE. Divide by n minus 2 instead of n minus 1. Weird. Okay, we don't have enough time to figure out why we do that. We just trust it. N minus 2 is the degrees of freedom here instead of n minus 1. Degrees of freedom is n minus 2 instead of n minus 1. Crazy, right? Actually, when you do multiple regression, where you've got more than one explanatory variable, degrees of freedom could be n minus 3 or n minus 4 or n minus 5 or n minus 6. It depends on the number of explanatory variables. With one explanatory variable, it's n minus 2. With 2 explanatory variables, it's n minus 3. I know, it's weird. Stats is weird a lot of the time, but that's the way it goes. You may need to learn multiple regression for some future class. You go on to get a graduate degree in economics or something, you'll probably need to learn about multiple regression. Don't throw your book away. If you have any inkling you might want to go to grad school for anything, Chapter 11 is about multiple regression, and it might be a good resource. We're not going to get to it really in here, except maybe to just say a few things about it. the last day or two of class. Not sure if we'll get to that or not. Can we calculate this? Yes, we can. We can calculate SSE. We've done that before. We can divide by n minus 2. No problem. We can take a square root. Definitely this is something that can be calculated. Let's do it. For the example we were looking at last week, let's see, it was this one here. And then Google Sheets, I can make it bigger just by doing this. There we go. Got different years, that's the X. You got different amounts of spending from the NSF, National Science Foundation, in billions of dollars. We can do regression on this. You should realize that this is not really an ideal situation for the regression model, mostly because this is really population data. For each year, there really was a specific amount spent. So it's not really a situation where you'd want to be doing inference, taking sample data and inferring information about a population. Therefore, this is not ideal for the regression model. But for the sake of simplicity, and because I only have 5 data points, we're going to go ahead and think about the regression model anyway. And then later, hopefully today, we'll look at an example where it's more valid, in some ways at least. So we did all these calculations. We calculated the sums, we calculated the means, x bar, y bar, we calculated the standard deviations last time. If you weren't here last week, you probably will want to look over that again. Watch me do it. It's something you should be able to do. I'm not going to give you an electronic assignment today for sake of time, but there will be one that we'll talk about doing next time that'll be due a week from now. And yeah, you might have to do some of this stuff. So look back at the old video. What's something that I want to do today? I do want to calculate these squared residuals. I could calculate the residuals themselves, and I do want to add them up to get SSE, and ultimately S. And I want to confirm that I got the same thing with this regression output that we looked at as well a week ago. So how do you calculate the residuals? Never forget this. It's the y value for each x value minus what? This was the tricky part. Y hat, yep. How do you find the y hats? You've got to use the regression equation. You've got to use the slope and the intercept. Slope is in cell B13, intercept is in cell B14. Just remember that. Probably is a good idea to use parentheses here, because I'm going to be subtracting the whole thing. Or you could distribute the minus sign through, but probably better to use parentheses. The slope in B13 times this x value right there in B2 plus the intercept in cell B14. Tracking with me? What am I using? I'm essentially using this formula right here. E being the residual, not the number E. It's error, residual. Actual y value, 40.1 here, minus y hat. Y hat's not shown here, we got to calculate it from the regression line. Slope times x, B2, plus intercept. I'm subtracting that whole thing, so I use parentheses, or else I need to put the minus sign through the parentheses. Then I'm going to square it. It's going to be a squared residual. Copy and paste. Add up those squared residuals. I can copy and paste the sum formula for this from this one over to the next column. There is SSE. That's the thing that's minimized by the least squares regression line, which you should know as well. Divide that by n minus 2. N is what here? What's n? 5 data points. So I'm going to divide by 5 minus 2. I'm going to divide by 3. Then take the square root. The regression standard error S, don't get that confused with the standard deviation. It's not the exact same idea. It's related. It's not the exact same idea, even though we're using the same symbol. The regression standard error, S, is square root of SSE divided by n minus 2, which is 3. There's the regression standard error, 0.563. Does it match our regression output? Yes, right there, 0.5633. In this regression output that I showed you guys how to get last time through that Excel Miner and analysis tool pack, you remember that? Those of you who were gone last week, you'll want to watch that. How did I get this regression output? That standard error right there, 0.5633, that is S. That is the regression standard error that I just found here. It's the same number. It approximates the sigma in those pictures that I just showed you. That was the standard deviation of all those normal curves. If the model assumptions are fairly valid, S is supposed to be a good estimator for sigma. So that's one new thing today. What else is new? We want to be able to estimate the population slope and intercept of the population regression line. And once again, I'll say it again for the sake of people on the video too, this is not an ideal situation for the regression model, so what I'm about to say is not really valid for this example. But for the sake of simplicity, okay, we're assuming it's valid, even though it's not really. Again, it's because essentially we have population data. We don't really have any inferential situation from a sample to a population. We've got the actual NSF funding. That is population data for each year. There's not a bunch of different Ys for every given X. There's not a bunch of different fundings for every given year. But in order to just understand the idea of the output, I'll go ahead and pretend it's valid. Okay? We want to read this output now. So far, what have we done? We know this is the correlation, this thing called multiple R, that's the correlation. 0.9911, I mentioned that last week. That does match the correlation right there, 0.9911. There's the square of the correlation. I guess I didn't put that up there. Don't worry about this adjusted R squared. We don't need to worry about that. There's the standard error we just calculated. There's n. That's no big deal. Number of observations. We're going to ignore the ANOVA part of this table for the moment, though we're certainly going to talk about that next week a lot. Today, we're only going to focus on the bottom part down here. We have already focused on this part so far that I've got highlighted. This came up on your homework. There's the intercept of the regression line. And there's the slope, even though it's not labeled with the word slope. Why would they not label it with the word slope if it's a slope? The reason is because if we were doing multiple regression with more than one explanatory variable, we'd have a bunch of different explanatory variables here, and they'd each have their own slope. So instead of calling them slope 1, slope 2, slope 3, slope 4, it's better to label it with the variable name that the slope is next to. The year, x, is the variable name that the slope is next to. So that is the slope. These are sample slopes, if we are thinking of this as a sample from a population, which again, we're not really, but pretend. This is not a beta 0 and a beta 1, it's a B0 and a B1. Sample statistics, not population parameters. But the idea is they're used to estimate population parameters. You hope that beta 0 is approximately B0 and beta 1 is approximately B1. Is that hope going to be realized? It can be if you do simple random sampling. so that your estimator is unbiased. And also if you have a fairly large sample size, so that your estimator has a small variability in its sampling distribution, a small standard deviation. The standard error that estimates the standard deviation is going to be small. Hey, look at the standard error. Those are standard errors. What are these standard errors for? This is SE sub B0. And this is SE sub B1. Those are standard errors of B0 and B1. What does that mean? Always remind yourself of these things. Standard errors. They're supposed to estimate standard deviation of sampling distribution. What are sampling distributions? They're normal curves, typically, that model the variability in the statistic from sample to sample. If you did many, many samples over and over again, either by simulation or by theory, or by actually doing it, which would be a real pain, you get many different values of the statistic, many different V1s for different samples. There'd be variability in those. This standard error measures that variability because it's estimating the standard deviation of that sampling distribution. There are the values. Okay, what can you do with those? You can do confidence intervals and hypothesis tests. How about the confidence interval first? Look at this. Lower 95%, upper 95%. Sounds like a confidence interval. And these are. Those are left endpoints and right endpoints, lower estimates and upper estimates for two confidence intervals, one for beta 0 and one for beta 1. You're trying to estimate the population parameters, the beta 0 and the beta 1. These confidence intervals are interval estimates for those. For beta 0, it's all negative numbers. We're very confident, therefore, that beta 0 is a negative number. For beta 1, these are all positive numbers. We're very confident that beta 1 is a positive number. These intervals are centered on these numbers. These two numbers, their average is 2.3. What's the margin of error? What if you did it in plus or minus notation? Let's write a formula here. Estimate CI to estimate beta 1 would be B1 plus or minus a margin of error. What's the margin of error? We're back to T. T star times the standard error for what? Standard error for B1. What's the degrees of freedom here? It's n minus 2, which is 3. We're after 95% confidence here. Look up in table D. I'm not going to take the time to look at it on the screen. You can look in your book. Look for 3 degrees of freedom. 95%. You're looking there with me. T star would be, I see a 3.182. 3 degrees of freedom, 95% confidence. 3.182 is T star. Take this standard error that's right here and multiply that times the T star, 0.17813885. Go ahead and try that product in your calculator right now. .182 times 0.1781 on 1385. The margin of error is about 0.57. So your confidence interval could be written 2.3 plus or minus 0.57. In interval notation, with this kind of rounding, you'd get 1.73 to 2.87. Do we have a match? Yes. That's about 1.73. This is about 2.87. So the spreadsheet output is giving you the answer, but you should be able to figure out the answer with the formula too, though we're still using spreadsheet output. Can this be done without spreadsheet output? Yeah, there is a formula for SEB1. It's not very pleasant. Let's look at that next. Actually, there's other ones that are less pleasant. Here's the formula for SEB1. This is the book's way of writing it. But I also want you to realize that you can write it in these three ways too. This is the way it's written in the book. What is S? S is the regression standard error, not a standard deviation. Though kind of similar to the idea of a standard deviation. It's the regression standard error, the formula from 10 minutes ago. Square root of 1 over n minus 2 times the sum of the squared residuals. That's S. And then you divide that by the square root of this summation. What's that summation? That's SSXX. We've seen that before. Which can be calculated, a reminder, as this. You can calculate it that way. You know, which formula you use depends on what you know. Okay? If you already have those summations here and here, and your calculator doesn't have statistical capabilities to calculate a standard deviation, it's probably best to use that formula for SSXX, and you plug it into here. The formula you use depends on what you know, what you have available to you. That's also equal to this, n minus 1 times the variance of x, the square root of standard deviation. That is a standard deviation. S sub x is the standard deviation of x. You square it, you get the variance of x. Multiply that by n minus 1, that's the same thing as SSXX. Why? Well, it's because of the formula for standard deviation. Sx is the square root of 1 over n minus 1 times these things. If you square both sides, the square root goes away. And if you multiply both sides by n minus 1, you see that n minus 1 times the variance of x is SSXX. I know I went fast. Something you should be able to follow if you think about it. And since the square root of the variance is the standard deviation, you can bring that standard deviation outside the square root and leave a square root of n minus 1. So this is a formula for SEB1. Hang with me here, another minute or so. That's a formula for SEB1. Should you be able to use it? Yes, you should be able to use this. Okay? You can calculate S. We did that, again, 10-15 minutes ago. You should be able to calculate SSXX. We've done that before. Or, with your calculator, you should be able to calculate this. Okay? This is a formula you can use. You can figure out the standard error and use the formula for the confidence interval. Give me still one more minute here. One more thing to mention. What about hypothesis testing? Where'd the whiteboard eraser go? Oh, it fell in the sink. Okay, another sink accident. What about hypothesis testing? I see a t-stat and a p-value. If you focus on the slope, the null hypothesis is the slope is 0, and the alternative that you're testing is the slope is not 0. It's two-sided. This is the t-statistic that you get for this test, and it can be calculated by doing B1 over the standard error for B1, which you can calculate. You should double check that. For this example, that would be good after class. You're still going to have n minus 2 degrees of freedom, 3 degrees of freedom. The corresponding p-value is right there, which you should be able to look up in the table as far as a range. It's about 0.1%, less than 1%. That's a pretty small p-value. We've got pretty strong evidence against the null that the population slope is 0. Though again, this is not really an ideal situation to use inference. We will do a more ideal situation next time. See you then.